Hey everybody! So welcome to week 10, and this is actually going to be one of our very last mini lectures, mini lecture 18. And for today's mini lecture, we're going to mainly focus on global climate change and the changes that have happened in the Holocene. So first, it's pretty obvious at this point in time that climate change is a super hot topic, and there is a scientific consensus that it is happening today. Now, climate change itself is defined as a new set of conditions that replaces the previous normal. Now, as you should have read, weather and climate differ from one another. So weather is our short-term variability in precipitation and temperature when we're talking about, for instance, how the weather changes every hour, whereas climate is the long-term average of those weather conditions, and that can be over years, decades, to even millennia, depending on how you calculate it. So we're looking specifically at those long-term trends and how they change. Now, in the lesson today, we briefly mentioned some of the causes of climate change on the long term. So I just want to review these briefly before we move forward. So first, plate tectonics, which we've mentioned multiple times this semester now, is when the continental plates are positioned in different areas, and this can have a big influence on climate. For instance, if the continental plates are positioned at high latitudes, they're going to be more likely to develop ice sheets than if the continents are placed near the equator. There can also be changes in the amount of mid-ocean ridge activity, which is also related to plate tectonics. So for instance, when there's a decrease in the volume of mid-ocean ridges, that can cause cooler temperatures. Plate tectonics also disrupts ocean currents. And so the way that ocean is circulating or the currents are redistributing heat can influence climate. Even photosynthesis on a very, very large scale at one point in time influenced climate because photosynthetic organisms use carbon dioxide in the atmosphere. The amount of chemical weathering can also have an influence on the climate. Chemical weathering also draws down carbon dioxide from the atmosphere. And then finally, the amount of volcanic activity can also cause climate change on the long term. Now, this is a list of what we would call, quote unquote, natural causes of climate change. So things that could influence climate change on the long term naturally. So I've mentioned carbon dioxide now twice already. So it's about time to introduce what a greenhouse gas is. You should have read this in the lesson already as well, but a greenhouse gas is a gas in the atmosphere that absorbs and emits radiant energy within the thermal infrared range. As a result, these gases trap heat within the atmosphere, and this is known as the greenhouse effect. Some examples of greenhouse gases include carbon dioxide, which is one of the biggest culprits that we'll be discussing today, methane, though, as well, water vapor, ozone, nitrous oxide, and chlorofluorocarbons are all included in this greenhouse gas category. So here's just a schematic. This is also in your lesson showing how the greenhouse effect kind of works. So we have energy, radiant energy coming from the sun, and it's reaching the Earth's surface. Some of that radiant energy will be basically absorbed by the Earth. Some of it will be reflected back and escape to space, and some of it gets captured and re-emitted by these greenhouse gases, and then it's held into the Earth's surface. Now, these greenhouse gases are actually really important to us. Earth is about 60 degrees Fahrenheit on average, and without these greenhouse gases in the atmosphere, it would be around 0 degrees Fahrenheit on average. So it's really responsible for the nice climate that we enjoy. However, very small variations in these greenhouse gases can drastically change the climate system that we live on. So before we move further, let's just touch on the carbon cycle as well and what influences carbon. So I mentioned carbon dioxide is one of the biggest culprits of greenhouse gas changes. So is methane, and methane also contains carbon in it, so CH4 is methane's formula. So it's really important for climatologists and geologists and paleoclimatologists, anybody that's studying this system, to understand where carbon goes, where it's stored, and how it's exchanged. So this diagram shows some of the basic portions of the carbon cycle. Everything in a yellow box is where carbon can be stored long term, and everything in a pink box is a flux, or a way that carbon is transported between the systems. So we can have carbon locked away in the atmosphere as gases in there. We can have carbon stored in the biosphere, which would be as plants or organic matter. We can have it stored in rocks or in the lithosphere, where it's stored as limestone, for instance. And we can also have it stored in oceans, dissolved in ocean water. And then all of those pink processes are just what happens to exchange them. So photosynthesis draws down carbon dioxide from the atmosphere and goes into the biosphere. There's diffusion of carbon between the ocean and the atmosphere. And then what I haven't mentioned is that humans are also contributing these. So in this diagram, we see that fossil fuel emissions from coal and oil and gas, which is a lithosphere storage, can be released back into the atmosphere when they're burned. So after talking today in our lesson, you should have learned that we've been looking at ice cores from Antarctica that are about 800,000 years old to observe carbon dioxide and temperature trends on longer timescales. This is just another graph that's been created from that data. This is from climatenasa.gov. So what we're seeing here are our glacial interglacial cycles. Glacial cycles have lower carbon dioxide concentration, while interglacial cycles, or warm phases, have higher carbon dioxide concentration. Now that's very clear from this plot. And what is also very clear is that carbon dioxide concentrations have not reached above a certain point for a very, very long time. Even further back, we don't reach carbon dioxide concentrations greater than 300 until about 5.5 million years ago in the Pliocene. So that just puts our current level of about 414 ppm in context of where we have been in the past. So it's been worth discovering what exactly is causing this change. Today, carbon dioxide in the atmosphere has steadily been climbing since about 1958. 1958 had about 315 parts per million, whereas today we see around 415 variably throughout the year. So that's a long-term trend that we've been seeing on a human timescale. And then carbon dioxide also varies seasonally. So you can see on this graph obtained from the Mauna Loa Observatory, which records and has been recording carbon dioxide concentrations in the atmosphere since the 1950s. So these are modern measurements with modern technology. And those seasonal variations, when we have higher versus lower carbon dioxide, those are actually related to plant activity. So plant activity draws carbon dioxide down in the summer, in northern hemisphere summer, and then lower plant activity when deciduous forests are less active occurs in the winter, which allows carbon dioxide to build up in the atmosphere. So those are just some examples of trends that we see today. Now we're going to watch a video here for a moment to put those trends that we're seeing since the 1950s in context. This is the Keeling curve. And the Keeling curve was developed in 1958. It's basically measuring atmospheric carbon dioxide concentrations in Hawaii throughout the year. It's the basis for much of modern climate science. Here's our seasonal cycle, where we have minimums as plants grow in spring and die back in fall. In 2013, we reached over 400 parts per million. Now it's showing us back to 1750. The yellow areas are the Industrial Revolution and World War II. Now going even further back, these are the atmospheric carbon dioxide records from ice cores. Again, you can see in context where we are. compared to the last almost 1 million years even. So looking at this information, we can compare this to human activities. Anthropogenic or human climate change is now accepted as a fact, and this is a graph by a paleoclimatologist. And so what we're looking at here is this orange line is a reproduced natural temperature trend that we would see given what we know about the previous 1 million years and glacial interglacial cycles. Now, at about 5,000 years ago, given what we know about the past, there should have been a natural start of the next glaciation if there was a world absent of human activity. However, what we actually observe is here in the light orange line, that's our actual trend, which coincides with early agriculture. Then we see a drastic increase as we have rapid industrialization happening in the 1850s. And then red here is the future possible activities that they've projected in this scenario. So let's go over how early human agriculture could have caused this trend to change from what we have previously seen in the past 1 million years. So first, humans began to agriculturally spread around 2,000 to 3,000 years ago. This included spread of rice irrigation, as well as massive deforestation efforts for slash and burn practices. The spread of rice irrigation, rice is actually produced in wetland environments. And in wetland environments, you produce a lot of methane. And methane is a greenhouse gas. So the spread of rice paddies or rice irrigation allowed methane in the atmosphere to increase. Furthermore, massive deforestation releases that carbon that's been stored in the biosphere back into the atmosphere immediately, which again also increases carbon dioxide concentrations. Now fast forward to the 1850s, our Industrial Revolution, and we begin burning fossil fuels. So coal, oil, and natural gas are all natural storages of carbon. And when you burn those fossil fuels, just like when you burn biomass for fires, you increase these greenhouse gases in the atmosphere. So the more we release our fossil fuels into the atmosphere, the more greenhouse gases we release into the atmosphere. Simultaneously, there are other things that are also polluting the atmosphere which influence climate. So smog, which is a mixture of smoke and fog, including ground level ozone, creates this urban haze. So this includes unburned hydrocarbons, and it's catalyzed typically by sunlight, and that can be very hazardous to human health. So for example, in 1952, there was a smog crisis in London where a layer of warm air got trapped cold air beneath it. And this kind of weather system lasted for about 5 days. And because the smog was in that cold layer of air that was trapped, thousands of people actually died of respiratory issues from this event, and even more died of complications after the smog. There's a picture in the top of smog from that event, and then in the bottom is smog from Los Angeles. So pollution has also depleted the ozone layer. There has been a slight recovery of the ozone hole, as we call it, but the pollution or the depletion of the ozone was caused by chlorofluorocarbons. These chlorofluorocarbons destroy ozone, and then that actually decreases the amount of radiation that's reflected back into the atmosphere. So ozone protects us from solar radiation. And so that allowed more heat to enter the atmosphere, getting trapped by those other greenhouse gases. So as I said, climate change is a fact. Here is a reconstruction from a free geology textbook of temperature change over the last 150 years, and we've increased by about 1 degree Celsius. There are lots of effects of these modern climate changes, so we're going to go over a few of these really quick. So first, These are things that we can actually observe happening right now. There's disintegration of sea ice shelves. I'm going to show you this video very quickly. So Arctic sea ice age is what's being shown in this. And they're showing age because age influences the thickness. So the older the ice, the thicker the ice. They've pointed out the oldest ice here. And we're going to see how that thickness has changed between 1990 to present day. The Beaufort Gyre is where ice is typically being reproduced. That's where the oldest, thickest ice is. The Fram Strait is where that ice escapes from typically. Okay, now we're looking at 2005. We're starting to see a reduction in the extent of this seasonal sea ice. 2008, the Beaufort Gyre is starting to fail. The thickness is very, very depleted. It's becoming extremely thin, and there's not as much of it. And these are measurements on our lifetime. And this year we're experiencing very, very thin sea ice. This is just another video of the melting of continental ice sheets. I'm not going to show this one. If you'd like to view it, this will obviously be uploaded to Canvas. But the main gist here is that the margins of this Greenland ice sheet in red are again becoming thin, just like that Arctic sea ice that we just watched. So what exactly happens to all that ice melting? Well, it increases sea level. So we've been seeing increases in sea level of about 1 to 2 millimeters per year. Also, those warm temperatures that are being produced from our greenhouse gases are causing thermal expansion of seawater because they are typically warmer. And so because of that, sea levels are rising slightly faster as well. The increase or influx of cold, fresh water into our oceans is typically what runs our ocean circulation now. So we have this kind of conveyor belt where cold, dense water comes in at the poles and creates deep ocean currents. And then water heated at the equator creates warm surface currents. However, if warm water moves poleward and is no longer replaced by that cold water, there's going to be a disruption of those cold deep water currents, and that slows our oceanic circulation, slowing the transport of heat around the globe. This will intensify tropical storms. So warmer air typically means more evaporation, which means more precipitation. So we have actually, with just a 1 degree Fahrenheit increase, you can get 4% more water vapor in the atmosphere, which increases the available water, which then intensifies our tropical storms. And also along with that, because we have higher sea levels, there can be much larger storm surges that surge further inland than we are typically used to. Furthermore, changes in our climate system in temperature and precipitation also shift our climate zones. So for instance, on the left, we can see our climate zones as they are today. In the northern hemisphere at the poles, we have tundra. We have some boreal forest below that, deciduous forest and shrubland. In the temperate zones, there's some desert or sparse vegetation, and then there's evergreens at the equator. Now what we see under a warmer scenario is a reduction of those tundra areas. You'll notice that Greenland is no longer covered in ice in the right image. There's expansion of deserts in certain areas. And there is an expansion of our shrubland in North America. Furthermore, there's melting of permafrost. So this is an example of what's called a feedback. So permafrost melting is actually frozen material in northern and southern limits. So this is found in the Arctic typically. Permafrost, once it thaws, it's filled with organic matter and carbon. That carbon that's been released from that as it thaws gets released into the atmosphere, and then it again increases surface temperatures, further thawing the rest of the permafrost. Another effect of climate change is ocean acidification. So when there's more atmospheric carbon dioxide, there's more that can be exchanged into the ocean. When there's a lot of dissolved carbon dioxide in the ocean, it interacts with the water itself, producing carbonic acid. Carbonic acid influences the way that things can create their shells. So a lot of little shelly organisms get really, really thin and their shells are deformed because they can't produce their skeletons in the way that they should be able to under more acidic ocean conditions. Another big thing is habitat loss. So climate and human pressures influence the habitats of organisms. The poster child for climate change has definitely been the polar bears, so I'm not going to stray, and this is a big deal because we just talked about sea ice loss, but their habitat is being destroyed. So they are looking for other ways to hunt, and this is causing some pretty brutal polar bear deaths, unfortunately. So on the right-hand side, this is a photograph of polar bears that are starting to try to hunt by scaling cliffs and getting these birds on these cliffs, because they can no longer hunt on the vast ice shelves, and most of the ice is very, very thin. So this leads me into our little discussion of the Pleistocene megafauna extinctions. So today we also learned about the Pleistocene organisms. Be sure to comment in that discussion this week so that I can answer any of your questions or give you information on the specific things that you want to know about these megafauna. But here's a typical image of what an environment might have looked like in the Pleistocene. There were predators, which you can see feeding on one of the elk. There were Pleistocene horses, which have been found in Douglas County. Mammoths as well, so we have multiple different types of mammoths that roamed, as well as mastodons. So this is a typical landscape. But what we see over time during the Holocene is all of these megafauna begin to go extinct. And so the question really is, what caused these megafaunal extinctions? And people go back and forth, and in my own opinion, I think it's likely a combination of these factors. But here's a diagram from a study that was looking at whether these megafaunal extinctions were related to human pressures, such as hunting, as well as pollution, things like that, versus climate pressures, such as warmer temperatures or drier conditions, or things that might influence the place in which that organism lives. So the consensus is that in Europe, climate likely put more pressure on these megafaunal organisms, and that caused them to become extinct locally. In North America, as well as Australia, the overwhelming situation is that humans possibly caused this extinction event due to hunting pressures. The brown animals in Africa, as well as South America, say insufficient data, so they were not able to determine whether this was a human or climatically impacted. But as I just said, and as this paper kind of corroborates, it's likely a combination of the two, humans impacting them by hunting as well as climate change. So another influence of climate change here moving forward is that there's an influence on the actual biology of organisms. So for instance, plant biology can be influenced by this, such as tree sap running earlier, more rapidly, and with lower sugar content under warmer temperatures. So if you enjoy syrup, you should hate climate change. Desertification, we've talked about deserts already, but desertification is caused as well or exacerbated by climate change as well as human activity. So I had one of your classmates mentioned that they thought that deserts were formed mainly by human activity. And there are natural ways that deserts form, but human exploitation and overgrazing of sensitive lands adjacent to natural deserts can cause deserts to expand, as well as changes in precipitation patterns, which are also caused by human climate change impacts. So for example, in the 1930s, the Dust Bowl in Nebraska was a combination of climate and human impacts. There was a drought that was occurring mixed with unsustainable farming practices that destroyed natural grassland ecosystems, And those grasslands have relatively deep roots compared to the agricultural crops that we grow. And so those deep roots really stabilize the soils, the loess that's in these areas. And because of that, there was no soil stabilization and it produced large dust storms. So there's a photo of that in the bottom, and then there's also an image of the extent of dust storm damage on the right. One more thing, so finally, increased forest fires is another effect of climate change. And again, this is kind of like permafrost where it feeds back into itself. So the more forest fires occur, the more carbon from the biosphere is released into the atmosphere, and that causes yet again further warming and more climate change. So here's just a map to show and demonstrate a model of how climate change is going to impact different areas of the United States. So the scale here is temperature change. So what that's showing you is red is indicating a change of about 1.5 degrees Fahrenheit increase, whereas the blue would be a decrease. Overwhelmingly, the entire United States is going to be experiencing warming. Nebraska specifically will focus on, so you can see that we'll experience about 0.5 to 1.5 degrees Celsius Fahrenheit increase throughout the state, varying on where you are. Simultaneously, precipitation will also change with this, as I mentioned. So a warmer world is typically a wetter world, but this is also influenced by atmospheric circulation patterns and local variability as well. So again, we're looking at the percent change. So the dark blue colors would be a higher percentage increase in precipitation, whereas the reddish orange colors would be a decrease in precipitation. So if we're looking at Nebraska and much of the Midwest, those areas are going to become wetter, whereas areas in the Southwest and in the Rocky Mountain regions are experiencing a decrease or drought, as well as in the Southeast. So just to summarize those patterns, in the Northeast, you can read through these yourself actually, but the place that I'm going to focus on here is the Midwest. So the Midwest, where we are, is in this area, is going to be experiencing some extreme heat, some heavy precipitation, which would lead to increased flood events. And Nebraska already has evidence of this occurring in 2019 when we experienced all of those floods in the eastern portion of the state. So that is all I'm going to discuss today on climate. And this is going to be, I think, our last mini lecture unless I post a few other things. But I hope you have enjoyed all of these lessons and these mini lectures. And let me know if you have any questions via email or in the lesson itself.